Today's webinar speaker is Professor Gabriele Morra. He is an assistant professor at the University of Louisiana at Lafayette since 2013. Before coming to the US, he had a rather nomadic career spanning 4 continents by working in Switzerland, Italy, Australia, and South Korea. Reflecting his unsettled spirit, his research moves subduction dynamics during his PhD at ETH Zurich to topics like exotic numerical methods in geodynamics, using the boundary element method, time evolution of the fractal properties of tectonic plates, and origin of the deepest earthquakes on Earth. In Louisiana, he turned his attention towards how we teach computing skills to our students. Based on the idea that adults, like children, learn by playing, he devised a series of hands-on strategies to help geodynamicists to become rapidly proficient in using vectorization and parallel computing in Python. Some of these methods are available from his recent book, Pythonic Geodynamics, Implementations for Fast Computing. So, Gabriele, take it away.
Okay, thank you very much, Lorraine. Thank you for the invitation. It is the first time that I do a webinar online, so I hope that I will be that it will be go fine. So if something is not clear or there is some problem, just feel free to interrupt me. So I just started with this first page. As Lorraine was saying, Pythonic Geodynamics is the title of this talk, and also of this book that I wrote not last year. So it is just a summary of many things that I've learned by teaching geodynamics to graduate students and sometimes to undergraduate students here at UL. So differently from other universities where I worked before, University of Louisiana is very focused on teaching. And in particular, the departments where I joined here at the beginning were just master-oriented program. They didn't have a PhD program. We will start next year with a PhD. So I'm glad that this starts, and I want to say to everybody who is interested in computational geodynamics to consider it. But the main point was that I was started to focus a lot of teaching, much more than what I did before. And by doing that, I've learned many things, many useful things for my career as scientist as well, not just as an educator, which is also very, very important. I'm very proud of this work that I've been doing this year. So here I've listed some of my main collaborators. In particular, I want to thank Ewan that encouraged me so much to write down everything I did to finish the book. Well, it is always difficult to finish a text that is 200 pages long. It seems to never finish, or 250 pages long. And all the students that are listed here on which I tested this material before presenting it to you. So motivation. As I said, computational methods and data analysis, obviously they play always an increasing role in our sciences. This is clear. I guess all the people that are into the audience are very aware of that. And what I've learned in these years, and by using Python to teach advanced numerical techniques to undergraduate and graduate students, required a much inferior dedicated effort to what, for example, it took to me to learn computational geodynamics. So at the time when I started computational geodynamics, I started my PhD in 2001. I finished in 2005. At that time, everything I wrote was either in C or in Fortran. And to learn, for example, parallel programming in MPI was very complicated. Basically, it took an entire PhD 4 years to learn all the techniques that you need to learn to understand computational geodynamics. It was very long journey, and technical obstacles were just every day very important. And debugging could take 1 week to solve a problem. And it was just very frustrating most of the time. And today, with these new tools like Python, but not only Python, many things can be done much quicker. And students can be trained in 2 years and not in 4, and that makes a big difference. So what is a big difference? So as I say, the main thing that I understood, also because I have children, is that adults, when they learn like children, they learn much better. So adults learn not so much, first they don't learn so much from frontal teaching. So what I'm doing now is just frontal teaching. You will not learn something from me, but you will get the information. But if you want really to learn something, to learn to do something, learn to become better and more proficient in whatever Python and fast Python, the only way to do it is to sit down and program by yourself. And so a program can be boring or it can be fun. And that's the main thing. If it is boring, of course, it's a huge obstacle. It's very difficult to do something boring for months or years. It's basically impossible. So one needs to find the fun in this. And one finds a fun in playing. Okay, children know this very well. Children learn things without you to teach them. If you try to explain something to a child, it won't listen to you. He wants to play, take something in the hand, something manual, and play, and they're the best learners in the world. So people don't learn by listening to others, they learn by doing and by taking really action. So when I try to develop these techniques for my students, I really, it was important that my student had immediately something small, like a little toy to play with, because I knew that they would learn something from that. While if I was giving them like a long code, very complex, and that they did not know how to manipulate, they would not learn anything. At the same time, if I was putting them in front of a completely white page and not know what to do, so nothing to have in their hand, it would have been impossible for them to learn. It would have been a very steep curve, like it was for me in a sense. So, as I'm saying, there are so about 10 years ago, there were not many textbooks in geodynamics. Really, there were probably Turcotte and Schubert, and then came the Introduction to Numerical Model of Taraskeria, which was probably the first book, was really easy to use and hands-on in the field of computational geodynamics itself. And then there were others that came a bit later. Other more, for example, like the book of Sadek and Takli or Bunge. And these books are more, let's say, in the traditional direction of geodynamics in the sense they teach a lot of theory. You need to have a very strong background in calculus to understand and appreciate that there is not so much about really the computation itself, how to implement the code by yourself. And then more recently, there are other books, like for example, the one of Becker and Kautz is not out yet. There is just notes online, but there is a lot of material there. And this is just book that just came out to Guy Simpson on finite elements. And many of these books, they focus on MATLAB. The focus on MATLAB, because it is true, it has been the standard for at least 10 years for students who wanted to rapidly learn how to program without going too much into the problematic of programming with difficult codes like C or C++. But there are many limitations, and I want to discuss them in this introduction. Now, how is high-performance computing taught really in universities? Before, as I said, there was just C, C/Fortran, C++. Today, things have changed. So it is a fact that Python is today among the new languages, so leaving on the side the one that are 30, 40 years old, they have a huge base of programmers. Among the newcomers, Python is the most used. But there are also other languages like Julia and Ruby and Scala, and all of them have different focus. But at the moment, basically, Python is the most compiled, powerful, probably because there are so many libraries and people had enough time to invest time to develop libraries, specifically for scientific computation. And that's because scientists have been the ones who use Python mostly for their work, so they developed the libraries that were necessary to do that. If you look today, for example, at university like MIT, in MIT, when you start, whatever scientific branch you take, it can be chemistry, it can be biology, it can be geology, you have to take, it's mandatory, the first year that you enter, you have to take Introduction to Computation and Programming using Python from John Gutak. So this is a course that they have to take. So this is, I think, is a very wise choice. I would like my university to do that too. We don't do it, but it would be great if our university would take the same direction, not to use Python, but to teach really computer science at the very basic to that 3 level. is a bit a skill that is as much necessary as calculus. And the early students learn it, the better they understand the fundamentals that you need to have to think in that way, and the better it is for the students who will be facilitating their future career. And also, if you look at other really important new tools, like for example, the one that is most in now, which is machine learning. And if you look at the main tools, for example, TensorFlow, that is the most used because it's the fastest, most efficient in the world, all the libraries are developed besides C only in Python. So you need to learn to use Python if you want to use TensorFlow, for example. So Python is really important and at the moment ubiquitous among the scientific community. So this to say that basically before people use MATLAB, and now Python is taking over. It's a bit like when Linux took over Unix. Unix seemed to be the standard like 15 years ago. Today it's all about just Unix, Linux. Now, what is really important in Python, then there are these libraries like Numerical Python, which are essential to write very fast and rapid code. In terms of visualization, Python is not extraordinary. Say it has more or less the same functionality of MATLAB, which has through a library called matplotlib. I wouldn't say this is the main reason to use Python, but it's certainly sufficient for what we need for doing science. What is really, really special, extraordinary, is that you can have tools, so Numerical Python to write the vectorized code that I will go into some details in a few minutes. And then you can write codes that can be very difficult to vectorize. You can use just-in-time compilation, which means that while you are writing, you are launching your code, although it is not a compiled code, you can say to the code to compile a small part of it, like a function that you know will take a lot of time and is not very well optimized. And Python will, while executing it, will compile immediately the little part very fast and will run it like a function that is compiled. It's extremely efficient, but one needs some more time understanding how to use it. And I will show an example today. Now, Python can also be parallelized easily. There are libraries like MPI for Pi, for message-passage interface, PyCuda for using GPUs, and the Plexi for Pi. So they're all very useful. And I will see if I can show today some example with MPI for Pi that I used in several recent works that I submitted recently. Okay, so there is the book. It's a picture of me, because I think you may not see very well me in the corner. At least you see me. It is the book that I wrote. That's my office on which I am talking now. It is the list of the points that we touch today. I want to first make some student cases. I want to talk about students that have been working with me in the past years, in part because basically what they've learned about how to teach depends on that. So I think it's important to mention that. But also to show how different it is to become a computational geodynamicist today, and what one can learn realistically in 1-2 years. And then after that, I will make like a journey into computational geodynamics, depending on the time that we have. We'll make a first eye view about the available distribution of Python that exists. I will quickly show something about visualization. And I will show what I mainly use for teaching, which is Jupyter. Jupyter is really an innovative platform. I think it's fantastic, revolutionary in the field, and I know that many people are using Jupyter today. I'm not using Jupyter Hub, and I've seen a presentation before mine that was from 1 month ago. I've learned a lot from that. I think I will switch to Jupyter Hub, but I'm not doing this yet. So I will show what I use now, which is just some standard Jupyter that is running on a server where all my students can access in a way maybe not totally safe for now. And then I will show some example of to use numerical Python and Cython in my course. I think this is the most important thing. It's essential of this webinar is more or less to explain what kind of technique I have been developing and using. And I think they're standard, but they're really practical and allow you to do most of the things that are done in geodynamics. Then I will show some nice example, for example, a Monte Carlo simulation of a volcano eruption, because you don't want to be bored with too much technical stuff. And then I will show something more complicated like operators and how can we transform operators into toys. Okay, let's move on. So student, for example, the first student that came to me, I think 3 years ago, 1 year ago, he finished and he went on to do a PhD, now in Monash. And he came to me that he was just an engineering background. So he didn't have any background in geoscience. He didn't have a background in physics, but he was working very, very hard. Of course, that's very important. But really, in 1 year, he could learn to program the particles in cell method. He learned this by learning Python, by learning numerical Python, and he learned at the same time to do geodynamics. It was all very quick, and we finished his master thesis with the very public geodynamics. Another student that worked with me was instead really in difficulty. The department sort of passed the student to me that he was really struggling to finish his master. And we could sit down, and he didn't program before. So he could sit down, he just had some experience with MATLAB, that was everything. And we could program together a software also with the Darcy flow, all in 3 months. We looked really at the questions, and out of the questions from the book, we could write a code. The code I wrote here on the left. I mean, the end, all his thesis was to write this code, which is 1 page. This code is only 1 page. It is able to calculate what you see here, which is the Darcy flow underground in a region where there is a very, very drastic change of hydraulic conductivity between faults, between shear zone. And this code it just worked. It just solved the equation that, Darcy flow equation that we have generally. But the point is that this student was able very quickly to write down the entire code. It runs very fast. We could run, for example, basically hundreds of simulations of this 2-dimensional setup and write a very elegant, simple thesis that allowed it to complete and go on, move on to its next project. Another experience that I had was also at the limited time, just a few months, but this was with some student who was more proficient in computer science. And they wanted to have an experience in geodynamics. So it was called the capstone work from a master in science and data science. It was basically the final work of their master. And they wanted to do something in geodynamics. So what we set up was an analysis of volcano seismicity. So we took the volcano of Villarrica in Chile, and we downloaded the data from OBSPy, show some example, and then we started to analyze all this using machine learning tools from scikit, the scientific kit of Python, and then we processed all of them, and we learned to use the simple simple really machine learning algorithm to detect eruption that happened on the volcano just by capturing this signal, this volcanic explosion, and to distinguish the signal from other signal. It was very, very fun, very quick. It took 3 months, and students had fun. I had fun. It was a nice project, and I think if I have a student who can stay a bit longer, can become really some interesting, serious new work in the field. Okay, so now that we looked at this example that I stimulated your interest, let's see a bit better how Python works, what you can do with Python, and how can one learn fast. This is a sentence from the Zen of Python, where there should be the rules that should be followed by Python. And they say readability counts. Simple is better than complex. Okay, this is a sort of obvious things, but it's better to remember that when one programs. Complex is better than complicated. Okay, so that means if the code looks very complicated, the problem is not complex. That means that the programming didn't do a very great job. If the implementation is hard to explain, it's a bad idea. And if it is, it's just plain, it may be a good idea. Okay, let's talk quickly about Python. Python was introduced by Guido von Rossum in 1989. It was released for the first time in 91. And Guido von Rossum was nominated benevolent dictator for life, which means he's, he can decide, can take some key decision when controversy arises. For example, that happened when we had to move from version 2 to version 3 in 2008, and it was decided that the version 3 was going not back compatible with version 2, which means that today we still have codes that run either in Python 2.7 or in Python 3 point something, and they may not work on both platforms. They have to be slightly rewritten. It's mostly input-output that's changed, but still often the codes do not work on both platforms, and two versions are necessary. And what they say, 2.6 will not be supported after 2020, which means if you have to develop a code today, just develop in 3.x. There is no reason to use the old Python. Okay, literature in Python. There are a lot of books. Think Python is probably for people who have started just to program and never programmed before. There are really a lot of tutorials, so we go more in detail in another page in the Python website. And for people who are interested in Cython, which is the compiled version of Python, then there is a cython.org. Now, the main two distributions that people use when you use Python today are called Anaconda and Canopy. Actually, it was when I started a few years ago. I have to say today, Anaconda seems to have completely become totally the standard, so it taken completely over. I don't know whether we remain like this in the future, but that's how it is now. So inside Anaconda there are many different things, from Jupyter to other way to editors and other tools. And this is probably the main one, because mainly the people that come from MATLAB, but also other people, really like this environment that is called Spider. So if you run Spider from the start, you have on the left, you see on the screen, you have the code that you're writing, and the right, you have at the top the variables that you're using, so you can immediately see what is happening, particularly if you have to debug a code. And the bottom, you just have the output. It can be graphical, it can be text of the code. So this setup, particularly if you have a big screen, is just ideal for developers and very simple, very similar to MATLAB, so for people that are moving from MATLAB. Now, things have changed very recently with the arrival of Jupyter. Jupyter, I think, is really revolutionary. It starts from IPython. So IPython stands for Interactive Python. And Interactive Python was basically a way in which you could write some instruction and have immediately a response. It is very good for testing new ideas, not for writing long code, but certainly for analyzing your data, when you work with large data, you post-process your model. IPython is very useful. Now, Jupyter is a bit of both. There is this interactive sense of interaction, but you can also write an entire code like in Spider. It's still not, you don't have these three windows like in Spider. Maybe they will develop, I don't know. But anyway, it is extremely useful for many things, and in particular for teaching. That's why I put it here and I emphasized it. Now, let's talk about visualization, and then when I will talk about visualization, I will show a couple of examples, and I will show you how Jupyter works. Now, Matplotlib is a main library that people use for visualization. It allows mostly to do two-dimensional visualization, but it can be very well molded and make it more flexible to plot, for example, things on a map. That there is a library that is called, remember myself, there's a library called the base map. And base map allows you to plot, all the boundaries of continents and countries on the Earth, and to plot anything you want to project over the Earth. So, for example, for environmental science, it's very practical, as well as to plot, for example, topography or geological properties. It's very simple and empty, and it's a bit like GMT, and it is as easy to use as GMT. You can also do further things. For example, you can create mesh. Here I show at the center of the screen, this is a Möbius string. You know, it's a string where there's only one side, although it has two faces because one becomes the other on the other side. So you can easily create it with a script in matplotlib and plot it, for example, in matplotlib. Or you can plot it with the VTK. I will show you in a second how to do that with the Parameter VTK. Another very important tools is OpSpy. I already spoke about this. This is a set of libraries that have been invented by seismologists, for seismologists, to analyze seismic data. And really, they are so simple to use that allows even a person like me who didn't have any experience with seismological data until 2 years ago to download a huge amount of data that are stored online in repositories like IRIS, and immediately in a few steps to analyze them, to cross-correlation of a master signal with a signal. That's how we, for example, detected the Strombolian eruption event, or do even more complicated type of analysis, spectral analysis of a certain kind, and try to do periods near related to eruption motion or to other known seismic activity. So it is really very simple, very practical to use, and it's all based on Python. Now, before continuing, very quick, I wanted to show an example on Jupyter, because I think it's very instructive to see things in action, not just a presentation. So now we try to share a page that I prepare where I open Jupyter. Let's see how many pages here. And I think it seems to be Google Chrome. So let's try this one. So, and here I will open Jupyter. There we are.
Okay, we're still seeing your presentation. If you're sharing your, there we go. Awesome.
Yes, can you see that now? Okay. Yes. So, for example, I will show something very, very simple to put this down a little bit. I want to show, for example, yes. So this is an exercise that I give at the very beginning to many students, to my students, which is to create the packing of a cube. For example, to take spheres and fill up a cube with spheres until they reach at least a packing of 50%. This is not an easy task, and but it's really not too difficult using Python. One is a good strategy. So you said in class we discussed at the beginning about the possible strategies, and then I let the student program their own technique. So once the strategy is clear, the programming is fairly short. It's basically just it goes from here to here. It's about 10 lines of code. That's everything. All the rest that you see here that I'm showing this Jupyter page is for visualization. That's why I'm showing this now. So how Jupyter works, it works really in a simple way. So the code is split in cells. So this is one cell, this is another cell, and in every cell, one can put whatever one wants. But typically, one will want to put in every cell a function, and then the code that is running here down. Now, when one puts something into a Jupyter Notebook, it is not code yet. So one can decide to run it just clicking over the cell and then say run. And then I'm running this cell. In this case, I'm just importing the libraries. And here I'm I'm running my functions so that I can use them later. Okay, so once I do this, I can now, for example, I will create a packing of about 50% of a cube, and then I will show you how to visualize that with ParaView. So here I'm creating, this is the code. What the code does is simply, it first creates some spheres inside my cube, and then when there is less space, you try to find a space where it's still empty, and it's adding another sphere there until it reaches and it fills it about up to 50%. So you found a very quick solution. It required about 1,000 spheres. And now I'm going to write a VTK file. What is a VTK file? It is VTK stands for Visual Toolkit, and it is a format to write files that can be read by software that use visualization. So in my case, what I'm creating now, it takes some time because I'm creating basically spheres, about 1,000 spheres, and every sphere requires about 500 channels to be described. So it took a few seconds to do that, to create this 500,000 triangles mesh. So now that this has been done, I can switch to ParaView and open ParaView and open the code that I just created. And that is, if I'm not wrong, this one I just downloaded before. And that is the outcome. Okay, so basically you can do this very quickly with a short code. That this is the way to create a three-dimensional packing of a cube. You can then slice it, for example, like this. I created this slice with a small routine inside Python, and this allows me to slice and, for example, use it if I want to create a Darcy flow. For example, I use it with my studio for some simulation of Darcy flow between this sphere and find the flow, how it circulates, to do a simple but interesting project. Okay, so going back now to the simulate, to my presentation, I go back here. Okay, so I do play show. Yeah. So this is probably the most important part of the talk. So how to make my code fast. Okay, so this is a nice sentence of Abraham Lincoln. Give me 6 hours to chop a tree, and I will spend the first 4 sharpening my axe. I think it is it goes really straight to the point. So of course it doesn't make sense to spend a lot of time to do your work. You want your software to do the work for you, and to make the work well. You don't want to wait days to have a result and then discover that maybe you have to tweak your variables a little bit differently, your parameters in another way. You want your code to be as fast as possible so you can make a lot of attempts, or you can create the Monte Carlo model that tries a lot of parameters and quickly find the solution that you're looking for. So it's very important to know how to make your code as fast as possible. There are some intrinsic limits, but there are also really always improvements that can be done. So what makes really a code in numerical Python fast? What should we do to make it fast? First is vectorization. So vectorization means really that you use huge arrays. I will show you an example. And when you use this vectorize operation, then you can do, for example, add 2 giant arrays in a very rapid time. Here I show an example. I create, for example, 2 arrays, A and B. And these are very large. I will show you in a second in Jupyter Notebook how this works. And what I do, I add them and in numerical Python using the broadcasting method, and obtain speed that are about 100 times faster than if I don't do it. So this means if I use standard Python and don't use numerical Python, I'm going about 100 times slower than what I could. So when I mean that I go so fast, I mean I like to say I go at C speed. So I go at the speed of a compiler code that will be written in C. As I said before, there are also the other option to write to compile a code. So to use, for example, a site implementation for very difficult routines that you don't know a priori how to vectorize. And that is, for example, is a routine that takes all the elements of a giant array and put them to 0. This can be vectorized. I can show you how to do it. But it's a very good exercise. And I make many examples in the book how this can be done in a non-vectorized manner, in a vectorized manner, or it can be done in a compiled manner using Cython. And the very interesting part, that using Cython, which is equivalent to compile the code really, is more or less the same as using numerical Python. Very close. It's slightly faster, because it's always a compile code, so it will always be a little bit faster, but it's faster of the order of a few 10%, 20%, 30%. Not something dramatic like an order of magnitudes. And of course, the way that is more challenging, but it's very important, is to go parallel. Today, we have access to all these supercomputers, and to have the possibility to go parallel with Python is very important. So I just wrote a paper in which I developed with a colleague in Australia, Peter Moore, a very very expert in parallel computing. We developed together a code for doing Lattice Boltzmann Method only exclusively in Python that runs perfectly linear on 1,000 processors. So this is very good. It's very important that this can be done, and to show that it can be done, our paper is now in review. And we just finished to write the 3D version of the code. So these are really important advances that allow many people to write really efficient and practical code using Python. Now, when you are teaching, what you should do when teaching? So, of course, you don't want to be too technical. You don't want to be too boring. So it's important to invent some exercises that are fun. So one exercise that I do and students really like is I propose them to create a real random series of 100 integer numbers from 0 to 9, and another one that is fake, in a sense that they take their finger and they start to randomly choose number between 0 and 9. So of course humans will not make a perfect flat distribution like the machine will do. But if you have only 100 numbers, it may not be that easy to find it out. And then what I do, I tell, okay, you create one series of 100 numbers, so they just create only the one you created with the random generator of Python, and then you put it online. And every student put it online without saying which one is the one generated by Python, which one is generated by them, and then all the others in the class, they have to find it out. It is kind of fun because they need to find a way, and the way to do it is not that easy. Because, for example, if you just try to calculate the mean or the average or the deviatoric, usually it will be more or less the same. And this is not enough. You need to really look carefully at the distribution, and after some time, when the student has the idea, there is a way that is really very simple, very effective to find out whether it's a human generator or machine generator. I'm not telling this to you. I let you have fun and find it by yourself. And when they find it, it's very interesting that you find out all of them. You find out immediately which one is human generated, which one is machine generated. So this kind of exercises really make to the student enjoyable to learn Python, to learn particularly numerical Python. Because to do this game, for example, they want something that runs really fast, that makes a lot of tests. So they're really careful in not writing the code that is a bit slow or silly. One of the problems that I have also in teaching is that I often have students that have very different backgrounds. So I teach at the same time in the Department of Physics and the Department of Geology. And so this means I have every year in my class students from physics, students from geology, and often I have at least one or two students from engineering. And so all of them have a completely different background, and it just cannot, it's impossible for me to teach them everything they need to know to do this class and to learn fast Python. It just will take a lot of time. And the only way to do it is to convince you to do some tutorials. So it's very good to find some very good tutorials that are very focused on something. You have found, for example, some tutorials that are focused on programming in general, or they focus only on visualization, or they focus only on numerical Python. And what I do, I give these tutorials to them, and I give them homework that are focused on each one of them, and they have to do it. And that's the only way really to force them to do some substantial work at home in the first weeks of the course, so that they all go to this, arrive to the same level, and then you can really work on some advanced topic. Otherwise, one remains always behind. It's very difficult to do some very interesting, stimulating work in modeling without reaching that level very quickly at the very beginning of the course. So that takes usually some friction. Some students are not that happy at this very steep start, but then they enjoy the rest of the journey. Okay, let's do some example that I also like to show to my students. They like it. This actually that you see now is the eruption of Vesuvio that happened in 1944, and I knew very well about this eruption because my father, he came from a small village that was very close here to the Vesuvio. He'd been down here, and he used to tell me when I was a child that he was born in 1941, and he told me that he used to play when he was a child on a mountain or little rocks that fell during the eruption, that arrived from the crater down to his village. And the people in the village, they collect all of them and they put at the center of the village and they build a playground. It was, Of course, people were southern Italy, middle of the war, very poor. There was no real playground, so they used to play there. And my father told me this story, and I always wonder whether is it really possible that all these rocks arrived there that far away. I know that this village is about 5 kilometers away from the crater. That's quite a lot. And so it came to my mind, well, let's check if this is really possible. And so the way to do it, and the way which you can, I've been teaching to my students to do it, well, first of all, you should have a good model for a ballistic trajectory. And so this is very useful exercise because they know already the solution of what is ballistic trajectory because they have done physics 1, so they know the analytical solution. And so they can quickly write the software that does it. And when they do it, they immediately realize the first thing. For example, they learn how to advect the particles. They learn, for example, how to choose the midpoint. It's not just to take the velocity at the time t and they calculate the position at the time t plus 1, because if you do that, you will not obtain the correct solution. You have to take the time, the velocity at the time t plus 1/2 to correctly predict the position later. And actually, if you do that, if you have a problem that is just like quadratic, like this, the ballistic problem, you will obtain the perfect solution. You will match exactly the analytical solution for this specific case, and this is very exciting for the student. They can exactly reproduce the analytical solution perfectly, even if they don't choose a very high resolution. And so this is an example of the exercise that I let them do. And once they learn to do this, I tell them to add also air. So to put also the friction of the air, which is very simple, it's just a simple drag law. The gist to add it just, is the density of the air for the area of the projectile for the square of the velocity. This is the traction of the air, so they can start to make something more interesting. They can model, for example, what happens. So what would happen if you would have be on the moon and there would be some ice following, as if you were, on Mars, and some ice were falling on Mars, and then actually some object was falling without air, it could kill you. And you can calculate all these little things, and the students really have fun with that. And then personally, I had fun in find out whether my theory was true or not. And I have to say that I still don't know, because together with the student, we made a Monte Carlo model with 5,000 launches. And this is more or less the result. What I plot here in the bottom is the distance from the center of the volcano. The volcano is here when it is at the position 0, 0. And each one of these dots is the point where the rock arrives to the ground. And so this is can be calculated immediately. You can see that it seems very difficult to reach a distance above 3 kilometers. But anyway, 3 kilometers is not that far away from 5 kilometers. So there might have been some very strong wind or some other effects that I didn't take into consideration. This is very, very simple ballistic model. Okay, so just I wanted to show you how this all look like very quickly on a Jupyter notebook. So we quickly show the notebook here, and now I should have learned to do it quickly. So this is that's the one. So let's see. This is not PowerPoint. I think this is yes. So this is the Jupyter notebook. So for example, what I was just showing, let me go away. Yes. For example, this is the Monte Carlo method. Okay, this is very simple to program. Just a couple of lines of code, and then the student they start to learn numerical Python tools to calculate the mean and the average. And this is the Monte Carlo simulation of a volcano. So they just had to learn to write the single launch, which they really had to work on that to calculate the exact solution of a trajectory of a particle, consider the drag of the air and every other effect. And then they just have fun in launching a large number of simulations. And they launched them very quickly, just 5,000 simulations, and they obtained the results, just the distance from the center. And the colors, I think they represent something about the initial angles at which they are launched, basically. So you can see that the one that are more far away are all similar. That's all. Basically, there is no way to go much farther than 3 kilometers. Okay. So I wanted to show now something that is very much more related to geodynamics, so continuum mechanics. So the tool that I teach always, that I start to teach with to students is a particle in cell. I really like to use particle in cell because they have to learn stage by stage Eulerian and Lagrangian advection, and then from there they have to learn how to solve the continuum mechanics equation, so continuity equation, and then the momentum equation. So it is really possible to divide in a step. So we always start with how to divide particles. So let's assume that you know, oh yeah, something happened. Let's assume that you know a flow, like in this case, you have a thinning flow in a box. And then you want to take an object, this for example, a circular object, and you want to make this turn around, so just follow the flow. And you want to do this as much perfect as possible. So there is a simple way to check whether this is true. You first make it follow the flow in this way up to a certain amount of time. Then you stop time, you invert your flow, and then you turn you basically let the flow going again. And so the whole time will reverse. And so instantly you should go to the equation. Now, of course, this is very difficult and challenging to do when you have, for example, a thinning flow like this one, in which you start from a circular anomaly here, and then you let it circle, and then it becomes very long and stretched like this, and then you have to go back and perfectly reconstruct it. In fact, if you try to do it just with the standard, without particles at all, without a Lagrangian model, but just with an Eulerian model, which you calculate the density of your field in a little cell, and then you advect this density, you can try a lot of different techniques. This, for example, upwind, that is one of the most used and advanced one. There are also high order upwind that work a little bit better, but it's basically very difficult to do. So if you have a thinning flow like this, that will arrive to this final configuration like you see in the second figure, and then you reverse it and you go back, you get something that is quite good, but it's very weird. On the contrary, if you use particles, so if you use, sorry, here this image is not displayed well, but you can look here at the figure. So if you use particle, you try to test the same algorithm that have been developed in the other parts that I was showing before. For example, for calculating the ballistic trajectory of a particle that is ejected from a volcano. And you start to use the same techniques in time, so forward, backward, or center, and the center is, of course, the most stable one. And you go and try that in a particle code, then you will obtain, and you take this thinning flow, then when you reverse the flow, you will obtain a result that is nearly perfect. So this is not the initial result, this is the result after all the flow is being advected this way and then reversed. So really, Lagrangian Eulerian method is what they are. So a mix of Eulerian method because your flow is described in a mesh, and Lagrangian because it's described in the particles, is really very efficient and a very robust way. And the nice things of Python is that it is very easy and very practical to use Python to do that, because the code is extremely simple and extremely compact. And I wanted to show one example. Unfortunately, this code, for some reason, they say there is a memory issue, but I have some other example here, and I will show them in a minute so you can see how the code looks like. Oh yes, here I have another example of the code. So this is how a standard routine looks like. So just with 8-10 lines of code, you can immediately describe the direction of a code. So this vectorized upwind is the example here at the top. But the sub here at the bottom is even shorter and even simpler than that. And so this very short code allows the student to quickly understand what is going on. It's really what I'm showing here an equation and the code, because really this equation reflects perfectly in this code. You can see here d plus and d minus are nothing else than the case in which this velocity is positive or negative. And then you just use this equation and you solve it straight away as you see it here. So this equation is perfectly mirrored into this code. And you write the code like you're writing really an equation. So to know a little bit of calculus will allow you immediately to write your function. Now, the greatest obstacle in really explaining continuum mechanics to students is to speak about operators. So really, this is something that many avoid to do in geodynamics books. I put here, this nice sentence, the people are in panic when they speak about operators because they seem to be very complicated, abstract mathematical tools. But I devised some very simple way to make students get understand and get close to use operators. So you can write functions that transform matrix into matrix. And they can visualize matrix very quickly in Python, like in any other similar software, just using, just showing the matrix as it is. And by looking at the matrix, how it is represented, they can build operator. For example, here I've shown how to build an operator to calculate the strain rate. This is the x component of the strain rate. Similar would be the xy and the yy. So it is just the operator is just the operator of an operator. So just a product of two matrices, in other words. And students, they come from background where they are not very strong in calculus. In the beginning, they are very intimidated by these formulas. But very quickly, they understand it's very simple. It is just really similar to just the calculus that they know, or to algebra that they know, because that's what you do with this operator. Operator just object that you multiply by each other. You just have to be careful to not to swap them. So when you swap two numbers, you multiply A by B, that's equal to BA. For operators, it is not always like this. Actually, it is usually not like that. But other than that, you can think of operators like numbers. And so you can operate them in the same way which you operate with numbers. So this is an example of an exercise that I do always, and students love it. That is to take a flow like the one before that we know, solve perfectly the continuity equation, and then to do that numerically. So here you have to write very carefully your operator in order to obtain here an error of 10 to minus 14, so which is, it would be the x and the x plus the y and the y has to be 0. And so only when the operator is built perfectly, the derivative operator, then this will become basically 0, or the machine error. And otherwise, it will be always very large. So as soon as the operator is slightly not tuned properly, then you will never get this error. You will get huge error, like 5%. And so students will have fun and play some tricks with that until they find the right solution. Another thing that's very important, that's why operators, we had to teach operators to students, even to geology students that want to do geodynamics, is that there is a big difference between sparse and dense operators. And so dense operators, if you use them, basically you make whatever code you're writing very slow. So we need to work with the sparse operators. And so it is really necessarily just a very simple exercise. You can take the 1D solution of a problem like a diffusion, and then you write your matrix diffusion, which is in this case A, which is sparse, so represented here at the bottom. And as soon as you try to calculate the inverse of 1 plus A, then you end up with B. So although I is sparse and A is sparse, so the inverse of this matrix is sparse is dense. And that of course is a big problem, because then when you try to work out and to make the inverse of this matrix, this becomes a very computationally demanding work for very large problem. And so they immediately realize the need to work only with the sparse operators. Once this is clear, they can step into larger, more complicated problems. For example, nonlinear problem. So nonlinear problem can be described by the same operator they use for linear problem. They just become a bit more complex, but the techniques are always the same. Once they've learned to deal with an operator that is in a linear system, they can understand the one in a linear system. And that's one of the, say, capstone project with which many of my students, they finish their course. So to write a software, they calculate the interaction of many spheres that fall down, for example, in a fluid. So these are very rigid sphere, very high viscosity into low viscosity medium. So you see that vector perfectly because they are decided by particles, but the solver can deal with this high nonlinearity of the sharp change in viscosity between the interior and the exterior of the particles. So the advector, they remain perfectly solid up to reach the bottom. or the opposite problem in which the spheres are very low viscosity, and they start to become like drops, and they start to cluster together and become like groups of I don't know how to call it. These are like, it will be like flames that are coming down, and these are more like plumes. If you would swap the system upside down, it would be exactly the dynamics of a plume. While this is, as you see, all particles, if they remain rigid, this is something that I described in the course, you can describe with the fundamental solution in 2D of one such particle. They basically interact even when they are very far away from each other. So they will always form a unique cluster, and they will fall down all together in one side of the box, unless the box is really very, very wide. So I see I have only a few minutes, so I basically finished to present what I wanted to say. I just want to say you can go on, and I have only one chapter in the book about advanced modeling in 3D. I don't go too much into the details of this, but everything can be done in Python. I implemented in Python integral methods in 3 dimensions with basically 3 representation and Lagrangian motion of your particles. And the really advanced technique that you also parallel on large. Again, here really the implementation requires only a few lines of code. For example, the integral of this green function, which are the fundamental solution of your equation, can be implemented only with a few lines of code, and that is the integral over one triangle. And then you have to sum over the integrals over the triangle, over the triangles. And this can allow you to calculate things. For example, I want to show just some example here. For example, it allows you to calculate what happens to tens of thousands of bubbles that rise, for example, in a fluid. It can be gas bubbles in water, or it can be bubbles in a magma, or clusters, or effects like this one. And it can also be used for causal dynamics that have been used very much actually already for calculating the stress due to faults in the crusts of the Earth. Already softened to this. So I arrived this way to the conclusions and say that students and professionals have now more accessible tools to learn programming. They are simple and accessible. These new languages are basically allow students to go very quickly into high-performance computing and modeling. Jupyter, I think, represents a real revolution. At the moment, it really allows me to teach so much better. Students love to have this interacting page in which they can change things and they can run whatever ideas they have on a page that's been already created by me. So they don't have to start really from scratch from a white page. By using Python, it is possible to do geodynamics in 2D using vectorization. In 3D, it requires some more work, some more expertise, but it's possible, in particular because it's possible to parallelize your code, and there are several tools to do that, all available in Python. It is very important that, one needs a good design, okay? So we need the code to be well designed from the start. It's important that students understand what vectorization is from the beginning. Parallel compute is available with MPI and PETSI. And I want to say students learn very quickly using these tools, and they immediately understand how computers work. And usually they see the fun of doing this work. And also some students show resistance, I want to say. It is just the problem is to make them to have fun. So when students show resistance, want to become creative, they just want you to give them exercise that are already done, that are easy to do. It is really important to invent games that are creative so that they can jump into that. I think it is 5 p.m., so I don't have time to show you more Jupyter, but I'm open to questions if people have them.
Great, thank you so much. That was a really fascinating webinar. I learned a lot about the history of Python. That was very interesting, and it was very interesting to see the sort of multiple problems that you're tackling and that can be tackled using Python in geodynamics. If you have any questions, please go ahead and type them into the chat box or indicate that you want to ask a question via your microphone. I encourage all of you to investigate a lot of these resources. A lot of them are very easy to install. I know through Conda, you can install Python and OpsFi and the Jupyter Notebook. Jupyter Notebooks is a great way not only to help you learn as a learning tool here, but also a great way to document your work and to reproduce your work, which is becoming more and more important in research these days. So I really encourage you to sort of explore and exploit that resource as much as possible.
Yeah. Yeah, if there are no questions, I just want to show you. This is the page that I use with my students. They really can start to learn how fast is their computer. It's a very simple exercise that they do always at the beginning. So they open this Jupyter Notebook, and they can see how long it takes for the computer to count to 1 million or to 10 millions. Because, you know, this is extremely fast. It takes about, for example, on the server, 6 milliseconds to count to 100,000. And of course, if they increase this number to count to 100 millions, it takes half a second. So immediately they know that, for example, it takes around, the machine is about able to count to about 1 million to millions in 1 second. So that's more or less the speed at which computers go. I see there are some questions. Maybe.
Yeah. So, yeah, same sort of questions that I had is whether or not you have a teaching site that you have these notebooks publicly available.
Not yet, but I would like to. Yeah, in fact, I would like to upload them, and definitely, I don't know whether it's better GitHub. I was thinking, I know that you also have on CIG the possibility to upload them, but I will certainly want to have them available to everyone.
Yeah, I do find these things as a great learning resources. I don't know how many people there are coders, but it's often good to have examples in front of you and to have snippets of code to cut and paste from. Mm-hmm. Certainly, if you would like, we are open to hosting your notebooks on the CIG servers, and that would be available to the community as well. We do have a notebook server for anybody else who's out there who wants to donate notebooks. And we do have a few for our codes currently on there right now, so we encourage you to explore those.
Yes, I will certainly upload them, and I will let you know.
Yeah, I don't see anybody out there wanting to know to be student number 2 who can write their thesis in 50 lines of code. I want to be that student. That would have made
you had to write 40 pages, but yes, the code was that short.
Yeah,
that you could do that.
Louise has a question.
Yes.
About sort of the resistance to coding from students. How do you try to make the exercises into a game, or have them find some resources of their own about programming?
Yeah, that's a very good question. Obviously, this is the main obstacle. So, of course, if students are really have fun and they're very engaged, that's an easy job to teach to learn. And the others are a bit complicated. So yes, of course, the first thing I do is to really invent games that are simple, so they feel more relaxed. They don't feel so intimidated. And that's the main thing. But yes, ultimately, they have to do some tutorials, because it's like some students do not realize that they have to learn by themselves. They think somehow teaching is passing something from me to the student. They wait this to arrive to them. They do not realize that they need to take action, and they can only learn when they become active. So in a sense, one has to force them in some way to do that. So the only way I found until now is to find this tutorial really well done and really explain them, and really give it to them, and really send them email and tell them they have to do them, and I give them exercise that are mandatory, let's say in a week, that depend on this tutorial, so that they have to do them. And I think anybody has the final solution for the resistance from the students, but ultimately the only thing to do is to make them become active. That's the point.
Kevin has a question with regards to basemap. So basemap is slated to become obsolete in 2020. Are there other packages you recommend? I guess there's a GMT Python, Cartopi. I don't know. I think one of the questions we have here is, are there Python packages that compare well to GMT, or do are people starting to use the Python interface to GMT
Yeah, well, I am looking for, I mean, I use a lot of GMT before using Python. And so if there was a really good binding GMT to Python, I would use that and nothing else. And so I know that there are several projects. So there have been several attempts to write this binding, and they sort of stopped after a while. They've been abandoned. But I know there is now a project that is really led by the University of Hawaii. So I guess this will become the standard, and when there will be the standard, I think everybody will use it, and absolutely this will be, I believe it will be the new standard.
Is that a binding, or is that a new Python package to, I guess?
I think it's only a binding for now.
Okay.
They intend to do a new development, that I don't know. I think it will be quite challenging, but they may decide to do it.
So how parallelizable is Python? I guess is the second question, and speaking to its efficiency as a code to write and as running on these HPC clusters.
So I found it. So it depends how big you go. That's my experience. So my experience is that I went up to 1,000 processors. And it worked very well. Yeah, I just wrote the code and with the paper and with something like Lattice Boltzmann Method, and it worked perfectly fine. Now, when I tried to step up to 10,000 processors, I started to have problems. Now, whether these problems, they depend on the binding with MPI, so the MPI for Pi, or whether they depend on some people wondering about the fact that to load all the modules, all the processors. I am not that proficient in that to say for sure. I know there have been experiments, and people found some that they tend to become slow when you go up to many thousands of processors. So I would say my experience is that up to 1,000 processors, it works fine, and people are working on that to go beyond that limit.
So it's a binding, I don't know if anybody out there knows, it's a binding on top of MPI versus writing in native.
Yes, but the instruction looks exactly like MPI. So they're really the same instruction in standard MPI. So they send to all processors and all are sent to, so there is a total control exactly like in MPI, if I didn't see. So the syntax is very similar.
Okay, so Raphael has a question. I'm not quite sure. Maybe, is there an option to manage a lot of simulation runs? Something you can track, use parameters and metadata about results, or some info about that run, something like Sumatra, if you're aware of it.
To manage a lot of simulations run, I'm not sure. So to run many simulations at the same time, basically. But I mean, well, one can start several servers. Yeah, that's a good question. So of course, if one runs in parallel, so embarrassing parallel jobs, one can run many times the same code, if that is what is meant. If there are many different Python codes, yeah, they can be launched separately from several, I would say, windows. They can be launched and put it in the background, and they will work independently. I think there should be no problem. I don't know exactly what the
yeah, I guess Raphael.
Management. Yeah.
Raphael, I guess the question is whether or not you're talking about in MPI environment or in Python. Maybe you can turn your mic on and explain a little bit more what your question is.
So, okay.
Okay. Well, great. Those are a lot of really, really good questions. Okay, another question. What are the options, resources available for calling Fortran code from Python 3?
I'm not sure. I know that there are many options for C. And I imagine that there should be also for Photon. And one of the problems with Photon and Python, I guess, the Python reflects really the data structure of C. So, so they really build all the arrays and build like in C. So I think there are some issues in passing large arrays between Photon and Python. But I'm sure there are projects. I'm not aware. I haven't been programmed in. I didn't program in Photon anymore since many years, so I'm not sure how to do that. Yeah, Numerical left to Python. Yes, I'm sure there are many options to do that. And so because there are so many of the libraries that exist in Python, they've been originated with software, for example, in Numerical Python. The origin from the 70s and 80s. So I'm sure there are options to do that. But I'm not an expert in this, so I'm sorry I cannot give so many indications.
Yeah, thank you, Julio, for chiming in there. There are lots of stuff in Python, and the website is a wealth of information. There are a lot of different projects out there and a lot of different communities. So Kevin says it's only available in Python 2 F2Py.
Yeah.
So.
You can, Kevin, you can also contact me privately. We can look together for something. So I don't have now the competence to respond to this question, but I can look into that.
Okay, well, thank you. I think we're running a bit over time here. I know it's past 5 o'clock over in Central Time. We really appreciate the extra time you gave us this afternoon to answer everybody's questions and all the effort you put together in this webinar and putting together your book and your course. They look like excellent resources. Next week, we sort of close out the sort of geodynamics in the classroom series with Eric Mittelstadt on March the 8th. Eric will give a talk called Where Have All the Dimensions Gone? Hands-on Methods for Introducing Students to Non-Dimensional Numbers in Laboratory Numerical Modeling. So we look forward to having you guys all back next month for Eric's webinar. And again, thank you, Gabriele.
Thank you very much. It has been really exciting to do this talk. I'm glad that there was a great feedback.